Hello, good morning.
Hello, good morning, George. Hi, Raghu.
Hey, Gilberto and George.
Hey, good morning. Hi, Anu.
Hey, George. Hey, Raghu. Hey, Gilberto.
Hey, Anu.
Hello.
I guess we'll give it a couple minutes more. And let's see. I do have a presentation. It's not going to take the whole meeting. I don't think it's basically a follow-up with what we're talking about, Raghu, and it was last week. But I was hoping we were going to have a new member, and I was hoping he would join. We'll see. Hi, Ryan. Good morning.
Hello, good morning.
Morning. Oh, right. Actually, I think you, yes, I was hoping you would join. Thanks for joining.
My pleasure.
Would you like to introduce yourself to the group, or I don't know if you have a few minutes to talk about that vision that you shared, or more than a few minutes? I mean, I only have a short presentation for this meeting, so we're not in any time crunch.
Sure, I can do it. I'll just do a brief one here today. I'm just want to gather information and see what all's going on here as well. So yeah, I'm Ryan Rackvick. Very nice to meet everyone here. I am an Intel rehire. I rejoined Intel Corporation in March of last year. So coming upon my 1 year anniversary. I worked at Intel way back when, from 2000 to 2005 in the microarchitecture research lab. My upbringing is CPU microarchitecture. I then went to the United States Naval Academy and have been a professor there for the last 18 and a half years in the Department of Electrical and Computer Engineering. My areas of research have branched out at the academy into other areas, still in computer architecture. I got to play around with FPGAs, GPUs, and most recently, computer security and machine learning hardware. And as I said, I rejoined Intel. I'm still in the East Coast, so I'm based out of the DC area. The objective, another colleague of mine, John DeVale, which I think I sent you the paper that he's actually going to present. He's leading that effort. We both rejoined. He was also an Intel boomerang. He spent time at APL, but we rejoined to kind of push along the initiative at Intel, getting into the MAG, military, aerospace, and government arenas with chip manufacturing. I'm sure you've heard a lot about that and have been involved in some capacity with that. But our objective is trying to have local DIB customers, defense industrial base, as well as government entities to help the transition onto 18A in particular, onshoring, manufacturing of 18A, as well as the follow-on nodes as it's coming onshore. So that's a little bit of my background. I can stop there, and then I can briefly discuss the chiplets stuff that we're specifically, looking at, and again, what we'll be presenting at GOMAC next month.
Does anybody have any questions or comments? I think that vision was interesting. I think for this group, I think it will be a nice conversation starter. But I don't know if anybody has any comments so far.
Yeah, I could just quickly introduce that, and we'll be talking a lot more about it at GOMAC. I don't know if you guys are going to be there, but basically the obvious observation that we made is, the cost and the business side of chiplets being an opportunity for the DIB customers. So the DIB and USG, basically USG will fund a particular DIB, Northrop, Boeing, Lockheed, whichever one it is, to design an SoC, and a lot of that IP can be reused, and it's hard to share IP for multiple reasons. You still have to complete that design effort, and the objective is to say, okay, we're going into this world where chiplets may become a thing. And a lot of the IP that the government will fund, Northrop will fund Lockheed to do, is, traditional IP that can be just shared. And instead of the government funding individually these companies to design it, to reuse common chiplets, not maybe special sauce, but common chiplets, specifically targeting what DIBs would be interested in, what government would be interested in. So not just, leaving it to commercial and letting it flow through that way, but instead targeting what, you would need for chiplets at the chiplet level for the DIB customers, and then reusing that across the DIB customers. So cut back on costs, cut back on design time, shifting some of it to packaging, but we also address, our ultimate vision is for this to be, plug and play. If we don't get there, reference design that can be shared and leveraged so that you don't have, because chiplets just shift a lot of the work, as you guys probably know, shift a lot of the work to package design, which is a non-trivial task as we're going forward as well. So the idea is to ultimately have a chiplet marketplace where you could reuse qualified chiplets for government use, but also make it easier for them to utilize these chiplets, because that's just one step, is having chiplets that are appropriate. The next step obviously is putting these things together and interoperability, not just UCIe, but the next step, what are you actually exchanging and putting this together to mimic an SoC. So at a high level, that's the whole idea, of our, and it's nothing really novel. It's more just, and I know a lot of people have been talking about this for years. It's just refocusing the effort, and, with a little nudge that Intel is here to supply and to work together to make this possible.
That's great. I think thank you for the overview. Your paper had some nice ideas too about the discovery of chiplets from that central controller, if I remember right.
Mm-hmm. So that's the ultimate vision, plug and play, where you have this controller that, similar to PCIe, that recognizes, what's coming on board, what everything is, handles boot and communication between them as you hop across to different chiplets, depending on your networking of them. But at this point, we're really just suggesting that you have to define the application space to know what these reference designs would be. You have to define the application space across DIBs. And that's the key thing. There's RAMP-C. I don't know if you guys are familiar with RAMP-C and the SHIP programs. And we're learning from those and saying, okay, what's the next step? What are the issues that we're having, in terms of SHIP, putting together multi-chips platforms? can it be used across, right? And the thing is, let's take a step back and say, let's design them at first, and we're not going to hit everything, and it's not going to be the most power efficient. It's not going to be the most performant. That's not the objective. It's to make it open the possibility to where we can cover a lot more designs in a cost-effective and time-to-market fashion.
Hey, Ryan, this is Anu. Nice to meet you today.
Nice to meet you.
I think the vision for this team here that George and Patricia run is pretty similar. And you're right. If you unless you go highly custom, it's possibly hard to get optimal performance, optimal area, optimal power. Also, it's very specific to an application. So, this team here is basically looking at HPC as an application and looking at potentially coming up with a reference architecture for a system which includes the pieces required for an HPC system and how can it be made to plug and play with, defining form factors, defining physical guardrails of powers and thermal and interconnects, and also the package too, right? Like you said, the package becomes non-trivial in these cases. So I think the ideas line up here. Just from my point of view, I know that George is very deep into what that compute kernel should actually look like, and that's been a lot of the focus here. But just if we took a few steps back and looked at it from a high level, I feel it aligns with what the group's vision is. George, does that make sense for you?
Yeah, no, I was actually going to say that we have been thinking and a little bit of struggling exactly with what you said, like finding an application space that this makes sense for. This makes sense for this showcases the capability, and we have some examples from HPC that we have access to because being a national lab, but it's it's hard to design a chiplet that is good for everything that we run. So we found two applications: high energy physics, particle tracking is one, and then also density fractional theory. These are open source. We have access to their code. We can analyze them. We can profile them. We can figure out their characteristics. In fact, what I was going to talk about today was along those lines. But yeah, we've been trying to tackle exactly the same thing as you were saying. Now, you might have different motivating applications in mind. I'm not sure, and
Yeah.
I'm going to lead you down to a different path.
Yeah, so we're definitely targeting the government space. So it's going to be different. So we were at I don't know if you all were at the Chiplet Summit a few weeks back, but the HPC driving this is a good thing, and any overlap. I don't mean to say that we're just focused on USG, because anything that's using FPGAs, there's plenty other sectors. Auto is obviously tackling this and hitting this issue as well. And anytime we can find commercial overlap, it's going to benefit everyone, right? So the whole problem that we're facing is the low volume aspect of government work. So when you have low volume, chiplets aren't as attractive business wise unless you can do things like this. Now, HPC is definitely driving this, but it still hasn't taken off, as you guys are fully aware. And there are a lot of challenges, both technical but also business wise, that are impediments to this. But anytime we can find, I guess my whole point here now is anytime we can find commercial overlap, whether it be HPC, that's also going to be a big win, a big win, and would help guide this forward. George, do you mind? Can you guys, I guess, just quickly introduce yourself?
Yeah, of course. So we can, let's see. So I'm at Lawrence Berkeley National Lab, and actually so is Angelos, who's at least on my screen on the other side of the participant list.
So you work with John Shelf?
Yes, correct.
Okay, because he's the one that we met with and been talking with, and we got introduced through a different person. that, in terms of just the things that we're doing to just try to connect and see if we can find overlap and come together on common ground.
Yeah. No, that's great, and that's how the connection happened. I mean, we've also been talking to some other vendors about this. I mean, yeah, you might have seen some articles about AMD going down that path and others, and it's great. I mean, we're OCP. We don't want to take sides like buy this product, buy that product, but
Yeah, sure.
But we are trying to figure out what we can do with this technology. I mean, it's easy to design an accelerator, but then what chiplets do you have to put around it to make sure it's not starved, for example? But that starts from profiling the application. Well, it starts from choosing the application, which we sort of done, at least for two of them. Then we have to profile the applications, see what the characteristics are, and then figure out where the technology is and where standards are, and either say, this configuration makes sense, or these are where the gaps are, and then do a similar analysis for other applications, and then see if we can design a chiplet configuration that covers multiple of them. We have
Great. So you're at Lawrence. Is everyone just
No.
at different places though, right?
Yeah. Hold on. So I'm just giving you a little bit of overview just from the
That's great.
side, and then we'll move on. But then what I was going to say is I had some. Yeah. So our systems serve like a few hundred projects. We cannot possibly design something that covers everything. So we have to figure out what the dominant applications are, whether in terms of time or resource utilization, like where it makes more sense to give the community capability to easily integrate something specialized as well, because that's where the big needs are. Okay, so I'll stop there. And Gilberto, you want to introduce yourself?
Yes, hi Ryan. I am Gilberto. I am relatively new to this forum as well, so I am still learning. I come from a company called OpenChip, which is based in Barcelona, Spain. We have European funding with the idea that we can design chips in Europe. I hope that's not an issue if you're working for the government. But in terms of the interest, is similar to what you're describing, Ryan. We do have a product in mind targeting HPC, but HPC, especially if you want to get started, is not that huge if you focus on that. My background also, before working for OpenChip, I worked for a company called Imagination Technologies that does hardware IP. And I spent quite a few years looking into the automotive market, where there was a lot of discussion, similar problem that you described, Ryan. There is not enough volume. They want something scalable for a small car, big cars. There are also a lot of discussions from IMEC, Mercedes-Benz as well has one guy, ex-Intel, that I've been following, that I talked to him, that they're also trying to standardize. And in terms of use case, yours and the others, any other thing before I let others talk is, I think it's good to focusing on application, but I believe that one of the things they're doing automotive is focus on the interfaces and things that are common, like power, how you reset the chips, how you bring it up. Because I think in line to what Ryan was saying in terms, it will not be perfectly efficient, but if we could come of, okay, you have this safe and this interconnect, put whatever you want, anybody can connect it, and then we have a starting building block from there. So I'll stop there. Those are my thoughts.
Well, very nice to meet you as well. So I did spend a little time in Barcelona. Intel actually had, in my previous life, my old boss started up research. So UPC is very well known in microarchitecture. I don't know if you know.
Who was your boss?
My boss, the one I'm talking about who started it, was John Shen. He was my grad school thesis advisor. He started it in the US, but then opened up a lab in Barcelona. And then my first year at the Naval Academy, I spent the summer there. So
you probably know OpenChip CEO. He comes from Intel. Is Fez Gim. So
what's his name?
Fez Gim. From Fez Gim.
That name does not. Do you know when he was at Intel? Because I know the Barcelona center closed, but I was there in 2006 for the summer.
He was probably working at that time in Barcelona Supercomputer Center, and then moved to Intel.
Supercomputer Center. Yeah. That it was in the same building.
Chat of mine, Ryan. I don't want to take all the one.
Yeah.
I'll put it on the chat.
we can move on. But I had friends in Intel Barcelona too. Well,
We can all meet there next time.
Yeah, I was gonna do sabbatical before I decided to leave the academy. I was there last January, back in Barcelona, and I was gonna be there for the summer, this last summer, but I got talked into rejoining Intel full time, so different track here. But sorry.
okay, thank you, Gilberto. Raghu?
Hey, Brian, and I think other Angelo, I think new. So anyway, my name is Raghu Shankar, and I'm an entrepreneur right now, looking at new things to work on. There are two areas that I'm researching. One is this whole area about chiplets. The second is cloud native. My background was like 17 years at Dell, where I was in the server product management and product planning. Then went and built, incubated the AI practice at Dell, starting in 2016 through 2020. Did some business development at Dell and then exited around 2023. And before that, I was at Intel in the silicon design and verification area. So my background spans both the semiconductor space as well as system space, and I'm also looking at a lot of the workloads. So yeah, so I'm looking at a lot of these HPC kernels and some of the HPC jobs at Perlmutter and see which one would be ideal for doing kind of a next level evaluation.
Great.
Okay, thank you, Raghu. Just going down the list. Anu, you want to introduce yourself?
Yeah. Hey, I'm Anu Ramurthy. I'm an associate technical fellow at Microchip. I also wear a second hat where I co-lead the Open Chiplet Economy subgroup at the OCP, and this is one of the work streams under that subgroup. We have 8 or 9 work streams. Some of them are very active. Some of them are, need some funding and need some help. But the whole focus is really how do we chip away at all of these pieces of a chiplet ecosystem in order to get more players, not just the people who can do it internally, like the AMDs and the NVIDIAs and the Intels of the world, but make it a little bit more of a democratized society. And one focus area is what these guys are working on is a modular architecture where you define the pieces such that you don't have to worry about, is this die-to-die interface going to work with somebody else? But it's a system where you know that if you put in your chiplet, and the secret sauce is inside your chiplet, but all of the connectivity is defined. And then, of course, with it has to go the software and firmware required, but an entire reference structure, which could be a potential to go forward. I've been in the semiconductor industry 25 plus years, and at Microchip, luckily my focus is similar at the chiplet ecosystem, how our products can benefit from it, how we can build our system solutions using chiplets from the products that we make ourselves, and then look to see how it makes sense to put that on an outside market. Really nice to meet you, Ryan. And I was thinking, with all this talk of Barcelona, George, the next time we meet, I think we should say it's in Barcelona.
That would help attendance.
That would be great. Sign me up.
Yeah.
I miss the jamon. I haven't had jamon in a while.
I go to some places. I'm sure food will not be a problem.
What's that?
I'm sure that the food will not be a problem if we meet in Barcelona.
Oh yeah, yeah. I miss it.
Let's see, Arvind.
Hi, Arvind Kumar. So I work at IBM Research in Yorktown Heights, New York. I manage a team which is focused on next generation AI. So naturally, we have been looking a lot at heterogeneous integration, packaging, chiplets, as ways that we can keep extending our AI hardware roadmap. With the continuing progress in all of the AI models, how do we keep the compute going? And particularly one thing that we've really focused on is how to speed up the development cycle, because it is very expensive especially for us as a research team, to tape out a full-blown SoC. And then as this field is evolving so quickly, to keep trying to tape those things out on a very short schedule, it's very challenging. So we think chiplets offer a very interesting opportunity where we could focus on, say, just the compute part of the chiplet, and a lot of the other things that we don't really want to focus on or don't have the resources to do so, such as the I/O parts. If we could chipletize them and offload them and let a company that is really good at doing that to do that, and let us just focus on upgrading, say, the AI core part, the computes, that would be of high benefit. And I have given a talk at the OCP last October. Unfortunately, I was planning to be at the Chiplet Summit. I had a bit of a personal issue and was not able to attend this year. I normally do. But generally the talks that I've given have really focused on this concept that we would take our SoC, we would break it up into chipletized pieces. Now we have two kind of goals in mind. As an enterprise company, IBM will always want to make sure that we are continuing on our enterprise roadmap and we're able to create high performance systems for our enterprise customers. But we're also looking at this as a big opportunity to diversify. And you mentioned the DIBs, and I think that was really very resonant with some of the many of the discussions that I've had also with these types of partners and with the U.S. government. That we want to be able to create smaller units, smaller building blocks that have open standard interfaces that can be heterogeneously combined with other chiplets. So we can't necessarily produce an HPC chiplet, but somebody else could. We can't necessarily produce a DPU chiplet, but somebody else could. And we do have some potential applications in mind. So we would like to even expand our scope from enterprise as being, of course, a priority, but also can we leverage that to make AI chiplets that could be combined and used for things like edge applications and other things that might be of high interest to the DIB members that you had mentioned earlier.
Absolutely, and we're definitely in heterogeneous camp. And George, you brought up before also about I'm at Intel, but our vision is open, right? In terms of this particular space, meaning other foundries, also participating and having different nodes available for different purposes in that final, product that you create.
Mm-hmm.
Okay, thank you. Kevin?
I normally work in EDA when it comes to simulation and stuff.
You're coming in a little low volume, Kevin. I don't know, you're far away from the microphone. So. If you can try again, Kevin. Now we're going to hear.
Can you hear me now?
Yeah, that's better. Thank you.
Yeah. Kevin Cameron, I work in EDA. My focus is OCP, sort of the tools that you need for building chiplet systems. And for OCP, my focus is taking the software workloads and trying to work out how to divide them up into more efficient, chip accelerator type stuff. So more software to hardware rather than trying to sort of make use of the systems that are there at the moment. It's how do we sort of reformat chips into chiplet systems and get the best efficiency for particular workloads. So I did a couple of talks for the Chiplet Summit on that kind of thing, but mostly the tool flow.
And you said you were where though? I'm sorry.
I'm independent.
Okay.
Like I'm looking at leveraging the open source simulation tools that are out there and federated simulation for verification, and then sort of digital twinning techniques for getting like software loads into particular accelerator chips.
Mm-hmm. Nice to meet you.
Thanks.
Okay, and last but not least, Angelos.
Hi Ryan, nice to meet you. So I joined John Salf's group in Lawrence Berkeley Lab like 2.5 years ago, coming from Greece. Apparently, a few of my colleagues in the research institute there also had joined in the past Intel Barcelona. So I heard a lot about that group. My interest, like I have a high interest in microprocessors, and you mentioned that, and and microprocessors and microarchitectures. I used to teach computer architecture back in Greece, in the University of Crete. My interest now lies also on multi-FPGA systems. I designed heavily on multi-FPGA systems that are directly connected without the use of microprocessors or PCI cards as usual. Nowadays, I'm also working on chiplet-related accelerators, and I also try to incorporate infrastructure and tools around the accelerator so that you can test and evaluate them properly. I was also at the Chiplet Summit, by the way, which was very interesting. Yeah, more or less, this covers it.
Nice to meet you.
So why don't we switch gears? I mean, this is along the same conversation, but we were talking, we had a meeting with our group, but we also have talked about this issue. Like, okay, so we have actually, what information do we need as part of this work stream to produce a design that is a concrete enough example that can come out of this work stream, and we can use it as a motivator. Like, this is what I think a chiplet should look like for density functional theory or something, because it'd be nice to produce a concrete example out of this work stream with the help of everybody. It's a group effort. But I put together some slides with some thoughts about the methodology, and I was hoping when the other half hour that we have left in this meeting, we can talk about that. And again, this is, let me slide share this. And and when I slide share, I cannot see the chat. Please chime in, stop me with questions, but if you put it in chat, I won't see it for a while. But yeah, it's a group effort. We have identified 2 applications. I have some other ones that I'm going to be profiling as part of another project, so that's going to be interesting. But your motivating applications are likely different, and you might have done some profiling, or somebody in your group might have. So if it's shareable, it helps. So the question here is how to design chiplets for a particular application, assuming we've identified some, and we have, but we could always use more. So the goal, what we're trying to do here is we're trying to go from an application, and that is what you see on the left. And when I say an application is, we don't necessarily need the whole source code. Of course, if we have it, we can profile it, assuming that we have a powerful enough machine to run it where it's meant to be run. But really, we're looking for some key metrics about the application. And that is what I'm going to be spending some time on in the next few slides. So we want to go from an application with some key metrics that it has to a configuration of a chiplet. And I know this looks like Legos, but the point is, like, we need to decide what we want there. We want an accelerator that makes sense. That is the first step. We have an application. We're going to design some custom RTL for it, for some of its kernels, for example. We might or probably will have some sort of general purpose compute somewhere in there as well. But the question is, what needs to be put around it such that, for example, it's not data starved due to memory bandwidth. It has enough memory. Or if it needs to talk to other chiplets, like it's a multi-node application, large-scale application, how does that communication look like? What protocols is it going to use? What technology, and so on. And then as a second step, as shown here, okay, so we designed a chiplet, but as I said, we have a diverse workload. Let's say that I want to design chiplets, one chiplet for 10 applications. And how does that going to look like? How are the resources going to be utilized or underutilized? We already have an underutilization problem in our systems today, even with general purpose hardware. And that is because we run applications with so many different demands. So can we talk about disaggregating some of the components of chiplets? So like if we have a node with like 4 of them, can one use memory that's located from another? That's going a little too advanced, but at least we don't have to solve that problem. There are many problems there, but at least we can showcase a mix of applications where something like that would make sense, just to motivate that line of research. Does this make sense? If you let me talk without stopping me, it's going to be over soon.
No, it makes sense. Yeah, that's
Okay.
when you start with an application, are you starting with software then, not the higher level abstract?
Yeah.
skills?
I mean, because we have software and we can
Yeah.
run it and profile it and extract those key metrics that I was talking about.
Sure.
If we have custom RTL, we can also use that. But this is not so much. I'm not talking about really the step to generate the custom RTL. There's a lot of work on that already. How to go from software, or at least an application can run generate some custom RTL. Whether that's high-level synthesis, whether that's a Verilog generator, people have done many things. It's about how to build a chiplet around it.
George, one question. In terms of what do you, and you probably discussed this before, in terms of the biggest challenge on this example you're giving there, are we more concerned of the size of the accelerator in ratio to memory or the interconnect? So I'm not sure if we are more concerned about the physical shape or that the performance will be suitable for multiple use cases.
I mean, you're right. That should also be put as a constraint. I don't have it explicitly here, but it makes. That's why I said like having multiple chiplets, because the application, for example, might require more memory than we have space for, and there's also the physical space, but also the power limit, and we can hit either one, and probably the power limit is going to force us to not have a lot of compute in one chiplet. I don't have any concrete numbers for that. I think some other meetings we talked about that, but yeah, the point is we're going to go from application metrics to like a set of chiplets, and then how we divide them depends on multiple constraints. Physical size is one of them.
I think, George, yeah, I think this is a good starting point, but I completely agree. And I had the same question or thought, which is that eventually you want to look at multiple applications and look for commonality of how you could produce, a set of chiplets that could do a large number of different applications. And, one interesting study, I think this was done some time ago by Lockheed Martin for for DoD type applications, and they filtered this down and said that at the end of the day, I think it was 17 different chiplets would cover like 90% of their applications. It was just a nice concrete statement that said that, okay, here's what we would have to do, because to create a chiplet for every application specifically kind of in a way defeats the purpose, but it also it's would be tremendously costly. So how can we consolidate functionality into a key set of foundational chiplets?
Yeah.
That sounds. Sorry, go on, Ryan. Sorry.
Yeah, that was a 2019 study by Lockheed. Yeah, absolutely. Yep. I mean, that's what we're suggesting as well. The more you're not going to get all the applications, but I would definitely second that. You want to try to get as many applications as you can, and there's going to be little branches of this. So, HPC target, maybe government targets, like in terms of the reference designs and the chiplets. It may not go across all these different diverse sets of area sectors, let's say, but the more applications you can get, the better, the stronger the argument.
Yep.
And one of the insights that we have been gathering for the last few months is we have been looking at a lot of the roofline analysis. I have collected a lot of, well, I'm going to say, I guess other people have done so, but at least I've been looking at it very closely. And we have looked at roofline analysis published at Fugaku for a lot of the jobs. And they looked at like almost 2.1 million jobs that they profiled. And we also got a similar study from Perlmutter, where they have looked at like 135,000 jobs. And what's interesting is, and these jobs span almost like 600 different applications. And these are all like HPC jobs running on either CPUs and GPUs. And they are also running for like long stretches of time over multiple nodes and different kernels, right? So what's interesting is 70% of the jobs, at least in the big sample sets that we got so far, are memory bound. And so when you look at the possibilities, and a lot of these memory bound jobs are also clustering in certain areas. And that's the next step that I was trying to work with George to see if we can identify some of those clusters, right? If we can find a cluster of jobs and applications that are memory. And so when you say memory bound, what it basically means is it requires a lot more data to do one compute. So there's a very, very key metric called arithmetic intensity, which basically can range from, say, anywhere from 0.1 to like 100,
Yeah,
right? And it can be even more, but a lot of these things are clustering around, say, 0.01 and 0.1. Essentially, basically, it means that you need to get like almost 16 bytes of data to do one flop of compute. So I think, so the question is, can I build a modular system where I can, and this applies to many of the kernels, right? So like LAMPS, some of the benchmarks, I think I at least got the benchmarks out there, like LAMPS and MIL-C, etc. And so the question becomes, can we then do a modular system where we keep some of the memory, IO, and DRAM and HBM common, and then kind of just bring in and bring out a different kernel and do the correct ratio of computer memory?
I've got to say that I consider HBM an anti-pattern. I mean, there's just no way it's a good idea to keep shoving
Oh, by the
more
way, sorry,
in the memory.
So okay, let's step back. Let's step back. Okay, so I think I'm just this is like basically what the papers have shown. So we can then decide what the right combination. We need to do that analysis.
I automatically assume if it says HBM, it's a bad idea.
Okay. Let's not try to design this on the fly. And I think that the
Yeah,
high level
it's more.
point
It's
is
like, okay, well, what's missing that's
the high level
that people
point
think
is
that's a
what's the
good idea.
combination of say DRAM, memory, HBM,
Well, you're not putting a
L1,
cost.
L2 cache, and look at the hit rates and see what's the best.
Yeah, but you need a cost on what it's costing you to move data around and what the communication cost is, and you don't see it in these graphs like the roofline. It's all about the flops and compute. So unless you actually measure what the communication costs are and the data movement
Yes,
costs
and
are,
all of that
you're
needs
not
to
going to
be
get the right answer.
correct, and that's the analysis that needs to be done, right? So but we have a starting point where we have very good sample sizes of like say almost 70% of the jobs are memory bound, and what's the right combination of chiplets we need to bring together to design a
Well,
most
you need
optimal
to
system.
break the workload down into sort of pieces, and because you write code at the level of routines, and the routines work with their memory, but their memory may not need to be shared with other things memory in the same application.
Right.
But we're
And that's a
not doing the
profiling,
analysis of how to break stuff up.
and that's exactly the profiling we need to do, Kevin. That's like what George, and at least I've been like discussing with George to say what kind of profiling we can do to understand what the data flow is, what the data set sizes are, what are the hit rates. So
And
I think
this,
the high level point I'm trying to communicate to the newcomers out here is that we're trying to get a good sense of what the job profiles are, and we have found that 70% of the jobs are memory bound.
so
Yeah,
let me,
I've been kind of known that for a while. The atomic Ethernet group is probably an area to look at for like measuring what it's costing to do the communication stuff and data movement. But Paul Borrell's Workstream.
so yeah, okay. So let's unpack a bunch of these things. We have the option to profile the entire application or kernels. Obviously, kernel will be more accurate, so we can design RTL, for example, an accelerator for a kernel, then design the memory for it, and so on. Makes profiling more work intensive, but it's doable, of course. This profiling is the big thing where it would be nice if this work stream can help, because it takes time, it requires access to code and systems, and we're trying to do some of this in LBL, but it's not going to be like, it's going to take some time, and it's going to be for a particular set of applications. But what we were saying is, so if folks haven't seen this, this is a roofline graph. It has the compute intensity on the Y and the arithmetic intensity. The arithmetic intensity is flops per byte. That's a common way to define it, which is how many floating point operations for every byte fetched from memory. There are other equivalents like instructions per byte, and that make more sense for applications that don't use floating point. We don't have many of those, but we have some. Yeah, for the application or dominant kernel kernels. But then if we have the floats per byte for the application, and then we know how many floating point operations happen, we can estimate the gigabytes per second, basically the memory bandwidth. It would be more accurate, of course, to get that from the profiling itself. That depends on the system, how we can get memory bandwidth from it. One way to do it is, for example, to get the misses from the last level cache. If the hardware gives us that, for the particular system, gives us access to that. At least I can speak for Pelmar. There are some counters on the memory side, but right now there's no way to access them, and that's something that they're working on. So we cannot directly get memory bandwidth from there, but we can estimate it from the cache or from the flops per byte metric. And that will give us memory bandwidth. Of course, memory capacity is easier. That the profiler tells us how much memory is.
You can also get the hit rates, right?
Yeah, that's what I'm saying. The last.
No, sorry, I mean, the hit rates I meant for the cache,
yeah.
not just for memory, just for the cache also. Hit rates for the caches.
Right. So yeah, that's what I'm saying. The last level cache miss rate is the opposite of the hit rate. But you can also get the hit rates for different levels of cache, I think. So we can also assume, like, if we go back to this figure.
And Ryan wants to comment something. So
Yeah, no, sorry, George. I actually have to drop off right now. But
okay.
Thank you so much for having me here.
Thank you. Nice meeting you.
Can I ask real quick, how often do you guys meet?
Twice a month. So basically every 2 weeks, same meeting, same time.
Okay. Yeah, if you're comfortable, please add me to the list, and I'll try to attend.
Yeah, I think okay. I'll talk to Patricia. Okay, yeah.
Yeah, so I don't think you have to actually be added, Ryan. Anyone can call in. The link is on the wiki page to the call, and we can send you that information. Yeah.
Yeah. No, I've sent that information already, but there is a group we can add you to that says reminders and so on. So
yeah. Okay.
Well, it's very nice meeting everyone. Sorry, I have to step off here.
Nice meeting you, Ryan. So yeah, if we get the cache miss rates for all other levels, we can also talk about some SRAM chiplet that we can use as a cache and figure out, because if we get the flops per byte, that is the gigabytes per second going out of the accelerator, meaning entering the cache hierarchy. So we can estimate the effectiveness of the cache, and that so then we know how many loads are filtered by the cache hierarchy, and then that tells us the gigabytes per second to the memory. So yeah, that's sort of our first step in terms of getting the compute intensity and the memory bandwidth. And then the other parameters we need for memory is the working set size, how big of a memory it needs. And the cache rates. Okay, I actually had the graphic that I just remember. So if we can get the gigabytes per second based on the arithmetic intensity, and if we get the hit rate from the profiler, we can estimate the bandwidth between the accelerator and the cache, as well as the bandwidth between the cache and the memory.
And my goal is to work out how to break the memory down into pieces so that you're not sharing it.
No, that's fair. I mean, there could be multiple levels of memory here. Yes, I know.
I mean, that's the kind of analysis I'm interested in, is can I like break down a large workload into a bunch of things I can put in containers?
Yeah.
Which, I can then sort of play with allocating containers to particular kinds of machinery and play with the networking between them as a separate thing.
Yeah. Yeah, those kind of, so if I understand right, you're talking about like a paging system, right? So.
No, I'm just the analysis. I mean, if I give you a workload and you start running it, how can I break up the memory within that into pieces so they're not interfering with each other? Because like, if you're multiplexing access to an HBM thing, it's just costing you an energy and time doing that. You really don't want to. You want to have sort of the memory that a processor uses. You want as little as possible, as close as possible, kind of thing, to make that work efficiently. Well, x86 is like a really horrible architecture, and GPUs are not far behind.
So Ryan, I was going for you, but what will be how would you improve other than sharing the same memory, time multiplexing, or whatever, what would be the solution?
Well, there's a lot of
Yours.
people doing in-memory compute. I mean, you can get computational
okay.
storage. The question is,
Okay.
okay, I give you a pile of computational storage. How do you allocate your workload into that?
All right. Okay. Yes.
You know, sort of
But-
like skill flux in people. You know.
By the way, so I don't forget, can someone drop the link of the paper that we mentioned about the chiplets, the 17 or so chiplets for the applications that this study of 2019 was mentioned? Just because we're making also a list of publications that are of interest. So if someone has the link, please drop it in the chat.
I have that. I mean, I have the paper. Let me actually just see if that was
Cool.
something that was publicly released. That's, I
Cool,
can check
cool.
out right now. I just don't remember.
Or at least just, yeah, if you cannot find it, just the title and we can probably search. Okay, thank you.
I do have it. I'm just want to make, before I drop it, I want to make sure that it is something that is publicly released.
Shareable. Yeah,
Okay,
Yeah, sure.
of course.
thank you.
Okay, let's see. We have 8 minutes. All right. And then I/O and power. So this is where some of the constraints that we talk about. I have power here, but it's also physical size constraints. I/O means moving from hard disk drives. You know, we should also think about those large areas of data movements, but it can also be. Oh, well, actually, scale is later. Yeah. So in this case, I/O is for hard disk drive, like basically the file system, as well as how much power all of these chiplets put together going to dissipate, and can we cool that? There's also, as I said, the physical size. Thanks for the reminder. And we can get the power per chiplet. So basically, when I say power, it will be estimate the power that chiplet that's going to run this accelerator will have. So we can estimate that based on how many operations, joules per operation. I mean, we need some RTO here, or at least we need some hardware model. And then for the data movement on chiplet, it has to be the physical distance. So, you know, this gets a little more complicated. We don't need to go there at this point. Obviously, the first two steps with the memory are going to be important. And then I/O based on profiling. But I think this is my last slide, just to finish out.
George, maybe one question on this. So like in this, no, on the next page, the I/O brown block that you're showing there, like I was thinking of these as each chiplets, and these are IP blocks or something on the chiplet, or maybe these are maybe each of these colored blocks like memory, accelerator, I/O are themselves individual chiplets. But I'm just wondering, when you talk about I/O, you know, we often are just talking about like the die-to-die interface, and of course we really want to minimize the picojoules per bit because those are going to be very high bandwidth. And then, you know, at least the picture that we've typically drawn is that there's a separate I/O chiplet which can handle getting off your system and package to something else. And then, you know, if you need to talk to PCIe or you need to talk to your hard drive or something. So that's why I'm just wondering if there may be some different layers of what we mean by I/O and how do we distinguish those?
Yeah, there are multiple IOs. What I was thinking with IO is the second thing you said. If you want to leave the package, go to hard disk, go to other chiplets like use the network and so on. But you're right. Yes, of course. Each of these will have need a way to communicate. Absolutely.
So would you envision that as a kind of a separate entity, a separate chiplet whose prime function is just to do that, to get you off chiplet, to get you off the package?
That's what I was thinking here, but
Yeah.
I mean, it doesn't have to be this way. And this is just one example.
I would say at this point, you know, there's a bunch of stuff in virtualization where you can virtualize all the network traffic and do metrics on it in the virtual space, and then like de-virtualize into real hardware if you want. So that's kind of stuff's there in software-defined networking. And if you work in Hyper-V and Azure.
Yeah. No, that's okay. Yep. And I mean, we can bring all those in, of course, and talk about how sharing and security is going to work. We actually did talk about that a few months ago, and it's definitely relevant when we're going to combine potentially and design a chiplet for multiple applications or with shared chiplets. But yeah, I'm not showing it here, but this is all things we should keep in mind. what was I saying? Okay, and then the fourth step has to do with scale out. So if you want to run an application that uses multiple chiplets, how are they going to communicate? And this is where the I/O comes in. So as drawn here, I/O is what every chiplet has to go through to get outside of the package, like go to the network. It does not have to be this way. This is just one example. But the point is, this gives us the escape bandwidth that I/O in terms of like for the file system, as well as I/O communication with other chiplets, which is basically what applications use MPI for, to talk to other nodes. That is what we need to support in terms of escape bandwidth for the package. And also tells us, because if we're going to design chiplets that are more computation intense, that they're going to put more load on the network. So that will give us some idea of what kind of network we need to support that. It doesn't have to be a system-wide network. It can be a node or a rack network, but some sort of connectivity between the chiplets. And I think that's it. So there are many great questions, and this is just examples. I did not mean to restrict the space at all, but it's as in terms of first steps, this is a good one. Let's find applications we can profile, and then try to follow this flow.
Hey, one other thing, George, is that I think the Perlmutter paper that I shared with you, right? They have used benchmarks, and some of the benchmarks could be a very good proxy for the applications. So we can, if that, and benchmarks are easier to run and compare against other same benchmarks running on other say systems. So that could also be kind of an option to look at, to see if we can run some benchmarks. Start some benchmarks and see if we can take that and profile it, and then see what's a good system to build around those benchmarks.
So yeah, that's what we're saying. Take application code, run it, and profile it. And this is where we need the help. Like,
oh, sorry, George. I think there's a distinction between an application code and the benchmark, right? So that's what I'm trying to distinguish.
Is anybody familiar with CUDA?
CUDA?
NVIDIA's CUDA.
Oh, CUDA, yes.
CUDA.
Yeah.
Yes.
Yeah, it's a part of what CUDA is looking at doing for you. It's like giving you a way to describe how the memory works. So basically, you have to flavor the memory when you're working with something that's a NUMA machine. So I think one of the things you need to do for this is to break the stuff down in ways where you can look at a particular piece of memory and how it's interacting with the code. And there was a thing from the DoD a while back. I put a link in the chat for performing automation of parallel program assembly. Just a mouthful. But the idea there is like, we can't get more speed and performance unless you go parallel, and you also have to go heterogeneous and like do application specific accelerators. But my view is that within a program, you've got lots of different pieces that are going to require different accelerators. So you have to sort of break stuff down into chunks of memory that are associated with accelerators, and then try and work out how you arrange that in the hardware.
Right. So yeah, if we profile by kernel, we can do that analysis. Yeah.
It's like working out what's going to be in a kernel. So basically, you're going to break it down and say, okay, I've got a pile of memory and compute. Looks like this chunk of memory uses this pile of compute. So you can say, okay, that pile of compute should go in some kind of kernel of its own. What do we need to do to build that kernel and make it work efficiently, which is the heterogeneous compute piece. Rather than saying, okay, I've got some kernels, what am I going to give them to do? Which is a slightly different problem. So
you talk about restructuring the application, if I understand right.
Trying to work out what the structure of the application actually is. So I work in circuit simulation. Circuit simulation is a lot of locality. Like you're only in, if you're in a floor plan of a chip, you can just divide it up and take a tile and everything's kind of local.
Right. Yeah.
How do I work that out in general, given a piece of software? If you give me a piece of software, can I tell whether it fits that circuit simulation like by the floor plan methodology, or is it doing something else? So if you do something like SPICE simulation, you're trying to solve matrices. So we're inverting and solving matrix stuff. That has a particular shape to it. The question is, what's the shape?
Right.
And how do I how do I identify the shape, get it into blocks that I can then allocate into particular accelerators?
Yeah. Okay. Yeah. I mean, I think we all agree there. It has to do with the structure of the application, and I know we're out of time, and that's why people are dropping already.
Yeah.
But yeah, again, this is if anybody can help with the profiling part, because yeah, we all know we should do something, but somebody needs to do it.
Yeah, you can profile in simulation.
Sure.
So there's a thing at checkerboard simulation where you just pick a piece and say, okay, I'll do that little piece in simulation, and the rest of it's running full speed. I mean, part of what I'm looking at here is like EDA designing chips is kind of stuck, but we can sort of tackle from the other end and say, okay, the software things we're doing are not very efficient. We can look at it as a different approach into EDA as to take the software workload and see if it can make it go faster. So you're taking code as the input for your process rather than like RTL. So you got something that runs reasonably fast. You just want to make it run faster.
Okay. Okay. Well, thanks, Kevin. I think yeah, this will do it for this week, and yeah, see you in 2 weeks. But I did like your comments about sharing and visualization as a way to make that safe. We'll get there. We'll get there. But
Yeah,
yeah.
I definitely
Yeah.
like the big picture and the big you have very good ideas, Kevin. So you have like the whole picture of things available. So it's very interesting.
Yeah, I mean, there's an awful lot of pieces to this. It's like, it's one of the things is like, okay, like I've got IPv6, but there's this horrible network stack that goes with it, so it's just really heavy duty. And then at the Chiplet Summit, Paul Borrell's group, we're looking at, can we do zero latency compute? And I was thinking, okay, like, if you want a then we're talking about removing the headers on the Ethernet packets and things. It's, it's like, okay, you want to do that, you kind of need to have both ends of a link and then some way to do operations on the link and say, make this link zero latency for me. And then like the network will adjust it and give you a lower latency thing rather than a high throughput thing. But at the moment, we just have no way to do that, so can't even ask about it, so. But we could do it in simulation. We could simulate that stuff in the virtual world. We could say, okay, like, tell me what I need to do with this in the virtual world.
Yeah. And then make custom solutions.
Yeah.
All right.
Something to do with AI,
Yeah. Okay, I think.
Okay.
Oh.
All right.
Yeah,
Thanks.
worried it's gonna be
Thanks for the
short,
time.
like very interesting session. Bye. Bye all.
Okay.
See
All
you.
right. Bye. All.
Cheers, guys. See you next time.
Bye.
Bye.